Okay.
Go ahead and introduce yourself.
Okay. Yeah, my name is Qing Li. So this is my thesis defense. The title of my dissertation is Detection and Defense Strategies for Anomalous Traffic in Wireless Networks. So this is a work I'm working under the supervision of my advisor, Professor Wei Chappie. So I will start with the introduction. So the problem we're looking at is wireless networks are particularly vulnerable to attacks due to their fundamental properties. So they have open median, and they have the dynamic topologies, and the wireless nodes have constrained resources. So the bad guys can get their hands on the wireless nodes and launch attacks, so especially denial of service attacks. So some of the attacks can be addressed by full-scale authentication. So you can check the authenticity of every packet you sent and received. But there are some scenarios you can't do full-scale authentication, because in order to do full-scale authentication, you need to have an infrastructure to set up and maintain the keys. So this is not possible for some scenario, such as multicast. So it's relatively difficult to accomplish a multicast authentication. So my dissertation studies the detection and defense of the attacks which can lead to denial of service attacks. So our solution provides lightweight solution to defend these attacks which can lead to denial of service. So denial of service attacks means authorized users are deprived of the service or resources they expect to have. So they can happen at different layers with different forms. So I listed some of the forms here. In my thesis, I studied 3 of the denial of service attacks here. So they are identity spoofing attacks, the routing disruption attack in the network layer, and the flooding attack in the application layer. So here's the outline of my dissertation. So we propose a multi-grade authentication scheme in multicast, which is called Dagger Tesla. And then we have the relationship-based detection, consistent check to detect spoofing. And then we propose SEAR to detect to secure routing in wireless Adhoc networks. So in today's talk, I will focus on the first project and the third project, and only give you a very brief high-level overview of the second project. So finally, I wrap up the talk with the conclusions and future work. So I will start with Staggered Tesla. So what's source authentication, and particularly what's multicast source authentication? So suppose we have a network here, such as the internet. So we have a sender, we call her Alice, and Alice is talking to several recipients, ABC. So there are many bad guys outside on the internet. They can do different things. They can change the data as they go across the network, or they can pretend to be Alice. So the problem of source authentication is particular concerned with these 2 issues. The first, you want to make sure that the data come from the trusted source, which is Alice. And then the second, you want to make sure that the data is not modified on the root. So let's go back to look at the unicast source authentication. There are several schemes you can use. You can use your standard digital signature schemes. This is based on public cryptography. A well-known example is RSA. But digital signatures requires a lot of computation, which is not suitable for scenarios where you have a real-time concern or you have computation restrictions. There's another approach which is based on symmetric cryptography. It's called message authentication code. So the idea is you have a key shared between the people who want to verify your message ahead of the communication. And then later, when you have this message, you use your key to calculate a short hash, which attach to your message and send to the party who wants to verify you. And then later, when he has the message, he can use the shared key to verify this message. So because hash is very fast to calculate, so message authentication code is computational efficient. So let's go back to the multicast source authentication. So you may ask, can we use digital signature? Yes, we can. They're very nice. But we still have the problem of computation overhead. There are several approaches has been proposed to do the signature amortization scheme to reduce the computation requirement, but at the expense of the complex schemes. So can we use traditional message authentication code as we did in unicast? So the answer is no. So let's look at the reason why. So let's revisit this scenario here. So Alice wants to talk to ABC, and ABC wants to verify that this message is from Alice. So in order to use message authentication code, they need to have a shared key. So in this group application, all the keys are the same key. So for one user in the group, such as C, so when he received this message, how can he know that the message is from Alice and not from any of the bad guys in the group, such as A? So message authentication code alone does not solve the problem. In order to make them work, the several approaches has been proposed. One of the most popular one is called delay key disclosure scheme. So because our protocol is based on delay key disclosure, so I'm going to focus on delay key disclosure here. So before I go into the detail of the delay key disclosure, the basic idea is, so Alice have a message. He create a message authentication code using the key, and then he send a message to the people, the party who want to verify his message. But he does not send the key out yet. Until a later time, he will send this key out to the receivers. This is a good idea because no one else can fake this message authentication code because they don't have the key. So until Alice sends this key out, they can start verifying this message. So I will start with the creation and the usage of the keys. So we break time into different time intervals, and I arrange key in such a way that I use different keys in different time interval. So this is the direction of the generation of the keys using a one-way function. So you can see here, in order to generate this key I-1, you use one-way function on this key and generate the previous key. So when I use these keys, I use in the opposite direction. I use from here to there. So anyone with this key, they can derive all the previous keys, but they can't derive any of the future keys. So I use another function f prime on my previous key to apply to get another set of the keys k prime. And these keys are actually used to calculate the message authentication code. The reason to use two layers of the keys is actually to improve security. For my key I use in interval I will release in a later time in I plus D interval. So for this period of delay, it's called delay key disclosure. And we use here D to denote this delay here. The most popular delay key disclosure scheme is called TESLA. It stands for Time Efficient String Loss Tolerant Authentication Scheme. So recall that I break time into different time intervals. I use my keys, different keys for each time interval. So for this first time interval, I use my key K1 to generate the message authentication code for all the message in this time interval. For the next time interval, I use key K2 and K3 and K4 and so on. So we have assumption that the network is of certain size. If we assume that all the packets sent in this first time interval have arrived all the receivers, so I now will start releasing my key K1. So all the packets you received after this starting point of here will be discarded. So this is security condition in Tesla. So I will reveal my key K1, and the receiver get this key K1. They can start authenticating the packets. So for next time interval, I will continue use K5 and release my key K2. So because I have to buffer all the packets during these 4 intervals, so I have a potential weakness. So adversary can try to conduct a buffer overflow attack. So that is a denial of service attack. So our work I presented here is actually to protect against this denial of service attack. So I will give you a cartoon to understand the delay key disclosure more. So we have two identity here. We have source in blue and we have the receiver in green. And now source wants to send packet to the receiver from interval I. And then he uses a key Ki from this interval and generate the message authentication code and send this packet out. So as time progresses, this message makes its way through the network. And now the receiver gets this packet. So what he do is he hosts this packet because he does not have the key to authenticate this packet. if you assume that this is the very edge of the network, there will be no more packets sent from interval I will be get accepted. So maybe also at this time, the sender will release a key for interval I. So until the receiver get this key ki, he can start authenticating the packets in interval I. So the question is, what if we release the key C earlier? So if we release the key C earlier, the receiver can have the C earlier, so they can start authenticating earlier. So let's look at what will happen if we release the key C earlier. So we have three identities here. We have source, receiver, adversary. Adversary is in red. So as before, S is going to make packets using key ki. So make packet for interval I and send this packet out, and the adversary gets this packet. So this does not help him much, because he does not have the key to forge the message authentication code. So if the sender decides that he will release a key seed for interval I here, and as time progresses, most of the key seed and the packet will make its way through the network. So now the adversary gets a key seed. So purple circle here denotes the area the key seed has been reached. So if the adversary has a key seed, if he has a fast connection to the receiver, he can make a forged packet and send to the receiver. So the receiver gets a forged packet, but he does not have the key yet, so he can't start authenticating the packets. So he has to hold the packet. So if we progress a little bit, and the receiver now gets a packet, and this is the very edge of the network, and there's no more packets from interval I will be accepted. And after 2 intervals, the receiver gets a key C packet, and then he can start authenticating the packet. So what we see here is both the real packet and the forged packet will be get authenticated. So this is problematic, because both of the packets will be get authenticated. So from the cartoon I showed just now, so if we release a key C earlier, there's people who can forge this message authentication code. We like to define what this area is. So we assume the adversary has zero forge delay and a zero link to the adversary. We want to give more power to the adversary in order for him to launch attacks. So from the security condition from Tesla, so packets sent in at interval I will be discarded if received after the starting point of interval I plus D. So if the sender sending out key seed at I plus T, which is T smaller than D, so all the adversary within this blue circle of radius D minus T can forge the packet and send to the receiver, and the receiver will accept this packet. So for the people outside this region, such as that adversary, they couldn't do that. People who can make the forged packet and get accepted at the receiver. So this area is called forge capable area. So the idea is the larger forge capable area, more adversary can forge the packet. So I will revisit this idea of forge capable later when I define Dagger Tesla. So any questions so far?
So clearly at the heart of this, at some point there's a little bit of public key. Can you describe where that comes in?
What? I'm sorry, I didn't get a question.
I mean, at some point there has to be some base authentication.
Oh, you mean the initial key commitment delivery? Yes. You need to, for the Tesla keychain, you have these keys, a set of keys. In order to verify this keychain, you need to send your initial key commitment to the receivers ahead of time. I mean, in order to deliver this key commitment, you may have your public key, private key peers to send using a signature. But just for that, only one key. Okay, so I will continue to talk the details of Dagger Tesla. So in Tesla, a message authentication code is attached to each packet. So here's how the packet looks like. So for interval I, we have message, and we have message authentication code calculate for this message using this key ki for this time interval. And we have a key delay disclosed for a previous time interval. So we have D, the delay key disclosure. So we release the key I minus D here. So in Dagger Tesla, we want to attach multiple message authentication code from the keys of the previous time interval to simulate that keys is released earlier. So here's how it looks like. So other than this MAC using the keys from this time interval, we use this MAC from the previous time interval. So the first question is, how many MACs can you attach to each packet? So because this key seed is released in this packet, so the maximum number of MAC you can attach is D. So remember here, originally in Tesla, for this key, I can use to authenticate packet for the previous time interval, but now I can use to authenticate this packet. So if this message authentication code is not valid, so my packet can be removed out of my buffer. So at the receiver side, he will start authenticating the packet's message authentication code as the key arrived. He will start authenticating from the lowest MAC and upweight to the up MAC. So at the receiver side, so when the receiver receives a packet, he will put the packet into the buffer because he does not have the key to verify. At a later time, when he received a key for this time interval, he will check the message authentication code for that time interval. If the message authentication code is valid, this packet is put into the buffer for the next layer and waiting for the next key. If it's invalid, and this packet is removed out of the buffer. So when the packet gets another key, he will check another MAC, and this process repeats until all the MAC has been authenticated, or any of them is invalid, is dropped out of the packet, or dropped out of the buffer. So as we can see, the packet is moving from the up layer buffer to the lower layer buffer. So the packet becomes more and more authenticated, and finally fully authenticated at this lower layer buffer. So packets are partially authenticated at each time interval as one key arrives. So let's revisit the forge capable area. So when I receive my first key, I will check my last MAC. This is the forge capable area. And these people within this area, they can forge the message authentication code. And only people outside this area, such as A5, they can't forge this MAC and get a valid message authentication code. So what it tells me is that this area is very large. So after I check my first MAC, I don't trust my packet too much because there are too many people who can forge this message authentication code. So as time progresses, I have my next key arrived. I check my next MAC, and my forge capable area shrinks. The trustworthiness of my packet increases, and I move from the upper layer buffer to a lower layer buffer. So as this time progresses, I have more keys. I check more of my MACs, and my forge capable area shrinks. And finally, when I check my last message authentication code, the packet is fully authenticated. So in Staggered Tesla, in order to remove a message authentication code for adversary A5, you need to wait for the full authentication delay. But now with Staggered Tesla, in order to remove a packet forged by adversary A5, you only need one interval. So we conduct several simulations to evaluate the performance of Dagger Tesla. So now I'm only going to give you one example here. So the simulation, we have three identities. We have sender, receiver, and the adversary. The interval size we chose is 200 milliseconds, and the delay key disclosure is 4 intervals. And the source is a source and sent out packet with average inter-arrival time of 40 milliseconds. We started different adversary sending rate. So for this column here, corresponds to different adversary sending rate. So 40 here means adversary is a Poisson source, send out packets with inter-arrival time of 40 milliseconds. And the infinity means there's no adversary. So from this table, when you move from the left-hand side to the right-hand side, adversary sending packet faster and faster. And because the delay key disclosure is 4 intervals, so total you can attach 4 MACs. So we studied the effect of attaching different number of MACs into the packet. So as you can imagine, if adversary sending out packet faster, you can expect there will be more packets in the buffer. So here's what we can see here. So when adversary sending out packets from 40 milliseconds to 2 milliseconds, the number of packets in the buffer increases about 10 times. But now if I attach 4 message authentication code, when it sends 20 times faster, the number of packets in the buffer only increases for 3 times. So we also look at the average inter-arrival time to remove a forged packet. When there's only one message authentication code, which is the original Tesla, it takes the adversary, it takes the receiver about 725 milliseconds to remove a forged packet. But if we attach 4 max, it only takes the receiver 125 milliseconds to remove a packet in the buffer. So Staggered Tesla really makes better use of buffer resources. So we have some theoretical calculation on the buffer usage. So I'm not going to the details of the theoretical calculation here. So the idea is we're using Qing theory to calculate the number of packets in the buffer. So this is the number corresponding to the topology we have in the simulation. These are theoretical numbers and number of packets in the buffer. So you can compare this table with the table we have for the simulation. This table, actually, they match each other. So beyond the basic Staggered Tesla, we also propose 2 extensions to augment Staggered Tesla to achieve full authentication delay. So the first approach is if the source has some protection of the region around him, he can take advantage of this protection and then to reduce full authentication delay. And the second approach is you can put additional key distributors into the network to reduce the full authentication delay. So I'm not going to cover the details here. So if you are interested or have any questions, we can talk offline. So any questions so far? Okay. So
assuming the authentication codes are small,
yes.
Versus the data payloads?
Yes, I mean for the message authentication code depends on the type of hash you use. Like for MD5 is 16 bytes, and for each MAC is 20 bytes. And for the packet, I mean, it depends on the packet size. But for many applications, such as multimedia, it's like over 1,000 bytes. So you compare the size, it's quite small. Okay, I'll move on to my next project. It's relationship-based consistency check to detect spoofing. So I'm not going to the details here. I'm only going to give a high-level overview of this project.
So what's the relationship between this one and the previous project?
This is we want to detect 2 types of attacks, which can lead to denial of service. Actually, total there are 3. Both of them can lead to denial of service. They happen at different layers. So we want to study this with lightweight solutions. The first one is the flooding at the application layer, and this is the MAC layer spoofing. So what is spoofing? Spoofing means a network identity, a network device is using the identity of another network devices. So is spoofing easy to do? Yes, it is. Especially in AODv networks, you can just change your MAC address using a simple ifconfig command. So spoofing is not too bad, but spoofing allows many other types of attacks being conducted against the wireless networks. So I list several of these attacks here. So we propose a set of strategies to detect device spoofing. And all of these strategies follow the idea called relation-based detection. So the idea is shown on the right-hand side cartoon here. So we have 2 devices, A and B, and they claim to use the same identity. And we have a monitor X, monitors all the traffic going on into the network. So there should be some relationship between all the packets coming from the same identity. And this relationship should be hard for the adversary to forge. So let me go through the story here. So we have device A. I want to send packets to monitor S, and he can only make blue packets, and monitor X will see the blue packets. And now B comes into the network. He uses the identity of A, and he also wants to send packet to monitor X. So here is what happened. So A sends this blue packets to monitor X, and B comes into the network. He can't make blue packets. All he can do is send red packets. So he will send red packets to monitor X, and A continues sends blue packets and the red packets. So monitor X will see this mix of red, blue packets. If he knows that the identity A can only make blue packets, so when he sees this mix of blue and red packets, he knows something is funny going on. So in the real world, we can't make blue or red packets. All we can do is to need a real relationship, something that we can quantify. So we propose several relationships which follow the idea of relationship-based consistency check. So they involve sequence number monotonicity, one-way temporary identifiers, the use of check analysis, and the multi-level classification. All of these techniques has been validated on the Orbit Wireless testbed. So again, don't have time to cover the details of this project. So if you are interested, you can either to go to read our paper or we can talk later. Any questions so far? Okay, I'll move on to my third and most recent work on secure routing. We propose a protocol to address secure routing in wireless ad hoc networks. It's called SEAR. It stands for Secure Efficient Ad Hoc On-Demand Routing Protocol. This work is in collaboration with Jesse Walker, Meiyuan Zhao from Intel, and E.J. Perry from CMU, and Yichun Hu from UIUC. So let's first look at the attacks on the wireless ad hoc routing protocols. So in wireless ad hoc networks, nodes can only communicate with other nodes within their communication range. So multi-hop routing is very important in order for a node to communicate with other people which are beyond its communication area. But the open nature of the wireless networks makes it very easy for an adversary to get access to the networks, and then they can inject, modify, or drop the routing packet in the networks. So the attacks on the wireless networks can be categorized into these two types. So the first is routing disruption attacks, which aim to prevent the packets being routed through the appropriate designed path. And the second is resource consumption attacks, which is aimed to consume the valuable resources at the wireless nodes, such as the computation, the bandwidth, or storage. The several routing protocols have been proposed for wireless ad hoc networks. So one of the popular one is called Ad Hoc On-Demand Distance Vector Routing, AODv. So because our secure routing protocol is based on AODv, so I'm going to give you an overview of how AODv works here. So AODv aims to provide the unicast and broadcast in wireless ad hoc networks. It's a reactive routing protocol. So node only discover a route to the destination when he has a packet want to send to the destination. So there's a two-dimensional routing matrix, the sequence number and the hop count. So I'm going to cover this two-dimensional routing matrix in the next slide. The routes are stored in each node's routing table to how to reach each destination. So this is a field consists in the routing table. So you have a destination address, you have destination sequence number, and you have the next hop in order to go to this destination, and you have number of hops in order to go to this destination, and lifetime of this route, and you have all the upstream nodes. So here's an example to denote all these fields here. So we have a wireless networks here, a wireless ad hoc networks. We have two sources, which are in yellow. So we have a destination, which is in green. So there are two paths set up between the sources to the destination. So for this specific node A, in its routing table, the destination address is the green node. And the next hop is this red node with hop count 2 to the destination. And the lifetime is the expiration of this path to the destination. And all the upstream nodes means all the nodes using this node A as the next hop to the destination. So in this specific case, for these two nodes are the upstream nodes, which using A as the next hop to the destination. So AODv use a sequence number to denote the freshness of a route, and also using this sequence number to prevent the routing loops. So higher sequence number means you have a newer route. So each node creates its own sequence number and maintains its own sequence number. So sequence number are monotonically increasing numbers. So there are only two cases you should increase your own sequence number. The first one is when you want to send a packet to a destination, you don't have a route. You want to send a route request. So before that, you increase your own sequence number. And the second case is you want to send a route reply in response to a route request. So there's only one case you should increase the sequence number of any other node by 1. That's when you detect a link break to that destination. For the hop count, so AODv considers that fewer hop counts means it's a better route. Any questions?
You say sequence number monotonic. Is that globally monotonic or just locally for each person?
Each person has its own sequence number, so he will increase his own sequence number monotonically. So you will have yours, I will have my own. You increase yours, I increase my own.
It eventually wraps around at some point, right?
Yes, depending on how large field you can use, but usually you choose very large, and then to prevent, when you wrap around, maybe some problems happen. So here's how AODv works. So when a source wants to have a route to the destination, he will broadcast a route request. So this is the field in the route request. We have the source address, destination address, route request ID, source sequence numbers, destination sequence number, and hop count toward the source. So as I said just now, source will increase the source sequence number, that's its own sequence number, before he broadcasts this route request. And each intermediate node, such as this node, he will first check the route request ID together with this source to see whether he has received this route request before. If he has seen this route request before, this route request is discarded. And then the node will check whether he has a newer copy of the destination sequence number than the one in his routing table. If he has one, he will put his own destination sequence number into this destination number field in the route request. And also the node will update the path to the source and set up the reverse path to the source. And this reverse path will be used later to send the route reply. So the intermediate nodes will increase the hop count, and then they will rebroadcast this route request to the next hop. So this procedure continues until everybody sees this route request or the time to live field has been expired. So after this procedure, every node set up the reverse path to the source so they know how to reach this source address. So in AODv, either destination or an intermediate node who has a higher sequence number or even equal sequence number with fewer number of hop counts to the destination can reply to this route request. So either the destination or the intermediate node will unicast a route reply back to the source. So for this example, is the destination reply to a route request. He will unicast the route reply to that node. And this is the field containing the route reply. So we have the source address, destination sequence number, hop count to the destination, and lifetime. So destination will increase its destination sequence number before he sends out this request. And for the intermediate nodes, they will update their routing table and to see whether this new request has a high sequence number or equal sequence number with a few number of hops. And they will update the forward path, which is the red path, to the destination. And then they will increase the hop count and forward this route reply back to the source. So destination will reply to every route request he received. He will send route reply to this node too, because he received a route request from that node. So as this route reply forward into the network, and the nodes set up a forward path to reach the destination. So one point I want to mention here is that, so once the source receives the second route reply, it will check whether this new route have a larger sequence number than the previous one. That's the high one. This is equal sequence number. But if it's equal sequence number, whether it has fewer hop counts. So he compares here, this route have more hop counts than that one. So this route won't be considered a better one. So he will use the original, this route, using sending to the destination. So in AODv, whenever a node detects a link breakdown, or he has a packet for a destination, he does not have an active route, or he received route error messages from someone from the next hop to the destination, he will send a route error. So we have an example here. So if this node detects that this link is breakdown, so he will send a route error back to this node, which this node using him as the next hop to the destination. And this node will check these route error messages and create its own route error, and then send this route error to the source. So all nodes are all unreachable destination using the same next hop count. The route error will be sent in one messages. So the format of the route error is you have the list of all unreachable destinations using the same hop count, same next hop, and the corresponding destination sequence number for this unreachable destination.
So for example, I guess a denial of service attack would be if someone could just say, oh, I have this wonderful route to the destination, send that back.
Yes.
And then say, oh, it doesn't work anymore, you have to restart.
Yes, you can do that. And also you can, I will cover a slide later on the possible attacks on the AODv. I mean, you can change the bad things in order to benefit yourself. And then later on, you'll be chosen on the data path. You can change the data or you can do whatever you want.
Is there any authentication at all from the destination? Is there?
No, for the AODv, no.
Actually heard of the destination?
Yes. So back to the question. So we see the attacks on the AODv here. So for all the messages I mentioned just now, there's no security protection at all. So adversary can get their hand into these wireless Adhoc networks and then to inject, modify, or drop routing messages as they are in the network. I listed several of these attacks here. So adversary can forge the route request, route reply, or route errors on other nodes' behalf. Sorry. They can also reduce the hop count or increase the sequence number as they forward this route request or route reply. So the purpose of the adversary to either reduce the hop count or increase sequence number is, in AODv, high sequence number means you have a new route, and lower hop count means you have a better route. So that's why they want to increase the sequence number or decrease hop count. So I'll give you an example to see how an adversary can decrease the hop count to launch attack. So we have a wireless Adhoc networks here, and there are two routes exist from S to D. So if all nodes are good, and this red node will be selected because it has few hop count. But now if M is malicious, and when he forwards this route reply back to S, he changed the hop count, which is 3. When he has 3 hops to the destination, he changed that to 1. And when S gets this message, he'll think, oh, M is a better route to destination than A because it has few hop count. And then he will select M as the next hop. And as a result, so the route containing M will be selected as a route sending data from source to destination. So he can do whatever he wants on the data packet later. Adversary can also choose to selective forward or reply to certain route requests, route replies, and all others. So because the selective forwarding does not involve any of the injection of new data or the modification of the new data. So this can be addressed by the intrusion detection mechanisms. So adversary can also launch one-hole attacks. This can be addressed by specific strategies such as packet leashes. So in secure routing protocol for AODv, is mainly address these 4 types of attacks. Questions?
Can you explain a little bit on comparing this with internet routing?
With
internet routing?
Internet routing
are
with...
any of these attacks not possible in internet routing?
In internet routing, I mean, for this route request, route reply, route errors is specific for AODv. For the on-demand routing discovery, if you don't have this, you have other routing messages.
I think you're not trying to address a very specific protocol component of AODv. You're looking more general at changing the routing metrics.
Okay, so if
Is that correct?
yes, so for the general internet routing, you have your routing message exchange between the nodes too. So you can forge these routing messages on others' behalf because there's no security protection as well. You can, according to your routing protocol, you can send a fake message. And also there are also hop count of the number of views you look at other, how many humps you can reach other destination. You can change that too. Because in most routing protocols, smaller hop count means it's a better route. So you can change that too. So the sequence number, maybe it's not used in some of the routing protocols. If you have something that denotes a better or new route with some numbers, you can change that. And for this too, selective forwarding and the one-hole attack is also applied to other routing protocols too. It's similar, but
said there are no protections. There are protocols like secure BGP and
yes, they do have. They do have the secure version of the routing protocols.
Can you use the same solutions in the AODv scenario, or is the problem fundamentally different?
It's kind of similar, but not the same. For AODv, because it's wireless Adhoc networks, one of the reasons we look at is because the wireless nodes do not have much resources and computation restrictions. For the BGP, and because they're very powerful, you can use a public key cryptography. So you can provide the asymmetry you want naturally. For wireless Adhoc networks, we hope we can have a lightweight solution to achieve this asymmetry of the authentication, but we don't want to use the public key cryptography.
Do you also propose to use public key cryptography
Yes.
sensor network nodes?
Yes, but lightweight is more preferred. That's why we look at this routing, secure routing, other than the existing. I'll go over two other existing routing protocols. Secure routing AODv use public key cryptography as well, but ours is based on symmetric cryptography. So from the example we just saw here, so we actually need authentication on the routing packets. So how about end-to-end authentication? Is that enough to provide all we need for this secure routing? So actually, no, they are not enough. So the question is, so how can intermediate nodes verify your routing packets if you only have end-to-end authentication? And further, for route error, it's multicast to all your upstream nodes. So if you can only have end-to-end authentication, how can the upstream nodes verify your message? So actually, we need a broadcast multicast authentication scheme. So I gave a brief overview in the previous project. So we can see that a lot of them based on asymmetric cryptography. So they have computation overhead, and maybe they introduce delay in the verification phase. So beyond that, so what can we do? So questions? So before I go into our secure routing protocols, I'd like to give you an overview of two of the existing secure AODv protocols. So the Bata proposed SAODv in 2001. So they want to provide the authentication for the route request, route reply, and route error messages. This is based on public key cryptography. So the assumption here is that intermediate nodes won't update the route destination sequence number in the route request, even though they have a newer copy. So this is a change from the original AODv. So for the change of this assumption, so the only mutable message in the route request and route reply is a hop count. And there's no mutable field in the route errors. So SAODv protects all the rest field use digital signatures and the route and the hop count using the one-way function. So here's the detail of SAODv. So when you want to send a message, you attach your signature and hash into your message. And for the neighbors, they will check the signature and hash to make sure that they are valid. If any of this is invalid, and your message is just discarded. So then you apply your hash function to the message you received to get the next hop and then forward this message. So SAODv supports both single signature extension and double signature extension. So for the double signature extension, is used when intermediate nodes to send a route reply. So the allowance of the intermediate nodes to send a route reply is called caching mechanism. So the problems of SAODv. Because SAODv use hash to protect the hop count. So the malicious node can still choose not to increase the hop count. They can forward the same hop count as the one they received. So this is called same hop count fraud. And because SAODv is based on public key cryptography, so a malicious node can flood a large amount of fixed routing messages into the network and to consume the computation resources of the wireless Adhoc node. So this is called signature denial of service attack. Because in SAODv, intermediate nodes do not authenticate previous hop. They only authenticate the originator of the message. So this is open the attack of formation of the routing loops. So I will give you an example to show so how this loop is formed. So we have a network here. We have source to the destination want to find a route. And now here M is malicious. And if he knows that A is upstream on this route, so when he sends the route reply to B, he will set A as a next hop to the destination D. So when B receives this message, he will check, oh, the next hop is to A and the signature is valid, and then forward this route reply to A. So when A receives this message and check the signature, valid again, and then the next hop to D is B. So the result is here, the packet will be looping between A and B.
Question.
Yes.
If B is getting the message back from M, why would
when M sends this route reply message, he can set the previous hop to be A. Because AM knows that A is upstream of this route. When he sends this route reply, he can set, it's in the packet header, you can set the previous hop to be is A. And there's no authentication for the previous hop.
we're not doing the reality check to find that's coming from M?
They don't check. They only check this is from D. So that's why SAOD have problem. They only authenticate they don't authenticate the previous hop. They only authenticate the original. So when B receives, he will check the signature of D and say, oh, it's a valid signature. He does not check is anything from M or from B. So that's why you can take advantage of this and formation of the routing loops. Sanjiri proposed another secure AODv. Aaron is in 2002. So it's very similar to SAODv. It's also based on public key cryptography. So in error, it used nonce plus 10 stamp to stand the freshness and the better route other than sequence number and hop count. So the route error is forwarded from the broken link to the source without modification. So this is the change from the original AODv. So in the original AODv, for each node he receives a route error, he will check this route error and then make its own route error sent to the source. For this, it's just forward altogether way up to the source. So this change is facilitated a type of attack. So I will describe in the next slide. So in Aaron, a signature and certificate is adding to the routing messages. So for the first hop of your source, you will check the signature is valid, and then you append your own signature and certificate into this routing message, and then forward to the next hop. And the next hop will check these two signatures are valid, and then they will replace the previous hop signature with its own signature and certificate, and then forward this message along to the source. So there are some problems with Aaron too. So because malicious nodes can still choose not to replace the previous signature, the signature of a previous hop with its own signature. Or they can even strip the outsider signature and only have the signature of the source and pretend they are the source. So this is the same as same hop count fraud. Because Aaron is based on public key cryptography, so it's also susceptible to the signature denial of service attack. So as I mentioned just now, route errors is forwarded from the break link to the source without any changes. So the adversary can take advantage of this and launch this error spoofing attack. So here is an example of error spoofing attack. So we have a source destination, and we have a route exist. And we have a bad guy, which is M. M knows that A used B as the next hop. And then he will pretend to be and send router error messages to A using its own signature. Because A will only check the originator of this router error messages. So he will check, oh, this is a valid router error messages. And then he will forward this message back to source. So this is the error spoofing attack. So any question? So I'll move on to talk about our protocol. It's called SEAR, Secure Efficient Ad Hoc Routing Protocols. So we want to provide the authentication for route request, route reply, and route errors, but we based on symmetric key cryptography. For the public key cryptography, only used in the initial key bootstrap phase, which is used to deliver your key commitments. The sequence numbers and hop counts are protected through the use of one-way functions. And route error messages is protected through the variation of Tesla. And Tesla already introduced in my first project here. We use the strategy from DSDV, which is another routing protocol that even sequence numbers are used for sequence numbers increased by the destination itself. And all sequence numbers are used for the sequence numbers which is increased by other nodes. So for this all sequence numbers, it will be used only for the route error messages. We also assume that there is at least one route from the source, each source to each destination consists of all good nodes. I mean, if there's an adversary can partition the network, there's not much you can do. Further, we assume that cache mechanisms are disabled, so only the destination can send the route reply to the source. In each node, they maintain two hash chains for itself to use. You have the authenticator hash chain and the Tesla key hash chain. All these two hash chains need to be created ahead of time before the communication starts. And I will give you an overview of this hash chain without giving the details of protocol here. So I'm going to give more details on how to use this hash chain later when I describe the protocol. Because this Tesla hash chain is the same as the one I introduced in the first project, so I'm not going to cover here again. So I will focus on the authentication hash chain, so which is very critical for this protocol. So we have a hash function and generate a chain of hashes. So this is the way of the generation. You have this value and calculate till the end of the values. So for each even sequence number, for each hop associated with this even sequence number, you should have a hash value associated with that. So we assume this is the hash value for hop count 0. For all nodes who has hop count 0, they should be able to derive the hash value for hop count 1. But on the other side, if any node who has a hop count 1, they shouldn't be able to derive the hash value for hop count 0. So because we don't want other nodes to decrease the hop count. So as a result, so this should be the hop count 1 other than that one, because you can derive from here to here, but not from there to here. So for each hop associated with even sequence number, you should have a hash value. If we assume that the network is total of m hops, so we should have total m hash values attached to each even sequence number. So I give an example here for sequence number 0. So if you have sequence number 0, you should have that hash for sequence number 1, because sequence number 1 is used to send your route error messages. So as a result, this value is for sequence number 1. There's no hop counter associated with this odd sequence number. It only used in send the route error messages. So the hash chain is broken down into m+1 group of values. Each is for one even sequence number and the one next odd sequence number. So for all nodes who have sequence number 0, they shouldn't be able to derive sequence number 2. So as a result, for the values for sequence number 2 and 3 should be on this side of hash chain. So anyone who has sequence number 2, they should have sequence number 0. But who has sequence number 0, they shouldn't have sequence number 2. So as a result of this hash chain, So intermediate nodes who has a sequence number couldn't derive a higher sequence number, which is the newer route, or they can't decrease the hop count, which means it's a better route. So as a result, but you can see here, we also use hash functions to protect the hop count. So intermediate nodes can still choose not to increase the hop count and forward the message they received directly. So in order to address that problem, we propose to add node identity into this hash chain. So this is, other than apply this hash function directly, as we have of this hash chain we apply to here and to get there, we propose to have the identity encoded into the hash functions. So this is an example when we have 4 nodes. So we have hash value hi, and each node encode node ID 0, 1, 2, 3 into the identity, and then they form this hash chain. And then this is the value of the next hash value. So when a node wants to use this hash tree, such as node 1, I want to use this hash tree to send my values, he will send all the minimum sets he used to the next neighbor. So the next neighbor can construct the next value, which is this value from all this minimal set.
So conceptually, you use like node identities like 0, 1,
Yes.
3. In practice, do you use like a black ID?
Yes, you can do that.
Is that what back to you?
Yes, I mean, it's up to you. You use your identity, you can use your name too. But something that identify that is you and not anyone else.
Why can't someone else use that identity?
No, because I'm node 1. I use my identity, and then I use this set. And if you are node 0, you don't have this value. You need your minimum set in order to generate that one. So when you receive I have my node encoding with node 1, and you are node 0. I send this set to you. You can't, if you want to set the same thing with the same hop count, you should have this node, and that node, but you don't have this node. So you couldn't send the same hop count with the same hop count I sent to you. Because you can't one-way function to have the set you need. Because you are pondering, you're not chain, you can't set this set. You should have another set.
What I'm saying is, in that figure, B0 and B1, right, both have HI. And why can't B0, the guy computing
Just put a 1 there
B0,
on the
just
end
put
of the string.
some other identity in that hash function? They both have HI, right? B0 and B1 guys.
Yes, they have HI, but they encode their identity here.
Right, but that is a public identity.
Yes,
So why can't B0 simply put a 1 in it and also get...
because B0 have is this set, this red node. He only have the red node. He does not have the whole tree. He does not have this value. He does not have this value. He only have this red node. From this red node, for node 0, he should have this, that, and that. But from this red value, he can't derive that one. This is the invert of the one-way function.
Okay.
They don't have this value. They only have the red one. So you can't construct this out from the red one. So you have to go to the next step.
So
That's the increase of hop count.
Node 1 actually somehow receives the hash of hi/1.
Okay, you mean
Is that
this one?
is that what you're saying?
No, I'm node 1. So I have this value. So I can construct this tree to have that value, right? So when I send this value for this hi, I don't use this directly. I use this red node. I send this red node to you.
So I think let's go back to the previous slide. Everyone has their own hash chain. All right, so as node 1, she has her hash chain. So now go for it. All right, so she has a hash chain hi. All right, and so from that, she knows how to now
Get the
encode her
next
identity
value.
into this. All right, but node 0 has a different hash chain.
I mean, he does not have this. He only have that. He only have this red node. So he does not have hi.
So the HI is not the same HI in all of them.
No, it's
Because I have this hop count, so I have this because I have the hop count associated with that. you are my next hop. So you don't have this.
What do we call that node on the left?
This authenticator for hash HI.
So node 0 is the node at the top of the screen.
No, this is someone who has this hash value for one destination. So suppose I have this HI for this destination because, such as this is H3, I have the 3 hop to the destination. So I have this value, but you are 4 hops away. So when I send to you, I will send this red node to you. You are 4 hops away, you don't have this H3, and you can't reconstruct this H3 because you only have those red node. So you can only reconstruct H4, which is this node here. So because you are 1 hop away from me, I don't give you all the information.
How many people in the room is this obvious to?
So,
No, okay, all right, so
so go forward with the.
I mean,
huh?
go.
What's unclear exactly is who is receiving what information. So the point is, I think right now is you're saying HI, this whole table is now just generated as a thought experiment by the person who has HI.
It's generated for each node, and then other nodes only know the hop they have
And you're giving a subset of the nodes
to the next hop. Yes.
Now exactly how you how you just determine which subset to set.
If I'm node 1, I will use my node 1 and the minimum set in order to generate the next hash value, the minimum set. So this one, I need that one, I need that one in order to generate that, right?
So I think maybe the way we should proceed, this slide and the previous slide is just meant to illustrate setup. It's actually not the protocol of what's going on. So maybe
Yes.
to actually show the protocol.
Okay. So
And then try to come back and refer to these slides to explain the protocol.
okay, I will continue to the protocol. So if you have questions after I finish the protocol, we can go back here to discuss. So for this tree we show here, so each identity, each node has their own hash leaf. So it's inefficient and expensive for large networks. So for small to medium networks, it's okay, but for each larger network, you need a very big tree, so it's kind of expensive. So there's another approach called gamma tuple hash values you can use to increase the efficiency use of this hash chain. So I'm not going to the details here, but the idea is for here, each node have their own hash leaves. But for the gamma tuple hash chain, you don't use one hash leaf on this hash tree. You have multiple, which is gamma. You have gamma copies of this hash tree. So it increases the efficiency use of the hash tree. For example, if we have gamma equals 1, which is you have your own hash leaf, you can use to a network of 8 nodes. But now if you use 2 copies of the leaves from the hash tree, you can use in a network of 28 nodes. So I will continue to the actual protocol. So here's how SEAR secures route discovery. So this is the format of the route request. So we have the source address, destination address, route request ID, source sequence number, destination sequence number, and hop count. So source will increase the source destination number, the source sequence number before he sends this message out. We have a little notation here. So we have VSJC denotes authenticator for node S with sequence number J and hop count C. So for this value is actually corresponds to one value on this chain we created for node S. So that is one of these values here, such as this value. We use there as authenticators. So if for this value, for the value on this hash chain is this minimum set of this red nodes. That's this